hop around the group. Our next talk is going to be given by Nadine de Campos. Nadine, were you going to present on your own computer, or did you want me to present for you in here?
I'm presenting on my own computer.
All right. In that case, go ahead and share.
Can you see it?
You can. So I'm going to go ahead and make you full screen here, and I'm going to mute us. And
Okay. Good afternoon, everyone. My name is Nadine de Campos, and I'm currently a first year of doctoral study at the State University of Campinas, Unicamp in Brazil. And this is my first time attending to the conference. Today, I'll be presenting one of my most recent research projects, the semi-automated mathematical characterization of central peak and Pickering basin using GIS and segment anything model. So this work was developed in collaboration with Álvaro Costa from the State University of Campinas, who's also my advisor, and with Caio Vilaça from the University of Lisbon. And this project has been underway for about 4 months, so it's very recently. In this presentation, I introduced the current implementation of the semi-automated toolkit designed to extract mathematical parameters from large impact craters. And this approach integrates the GIS-based space analysis with these modern computer vision techniques. So, mathematical parameters are very essential for understanding impact mechanics and planetary surface evolution and for estimating the relative ages of planetary surface. However, traditional manual methods, commonly applied on Sirius and Mercury and many other bodies, can be time-consuming and less efficient and more subjective. And as planetary datasets become larger and more detailed, there is a growing need for tools that are faster, more efficient, and adaptable to different regions and crater types. So here we have the ultimate methods that can reduce process time while maintaining both precision and flexibility. So because of this, we started to develop this QGIS-based toolkit for the semi-automated measurements. It's a Python-based toolkit and was developed for extracting mathematical parameters from digital elevation model and some remote sense imagery. The toolkit enables measurements of diameter, depth, central peak height, as ring diameter, and Pickering height. And while it's adaptable to any planetary surface, our initial testing has focused on craters on Sirius and Mercury, more specifically here on the complex craters on Sirius and Pickering basins on Mercury. I will talk briefly about the segment anything model. So SEN, it's an AI model developed by Meta AI, and it's a powerful image segmentation model designed to identify and outline objects with images. And it's very interesting because it uses a variety of input prompts, commands that specify what to segmentation in the image. So basically, these prompts allow it to perform a wide range of segmentation tasks without needing additional training. So this is really interesting. And it's specifically useful in planetary science as it automated precise delimitation of landforms, such as craters. So this toolkit we are making this integration with this with the segment anything model with our toolkit through the GeoSen plugin developed by Zhao et al. In 2023. GeoSen is very interesting because it enables real-time and interactive segmentation of large impact images in QGIS, support high-resolution analysis, and even on standard hardware. We can see here in figure 1 of Halley crater on Sirius. This is the one of the youngest impact craters, and this green line represents the segmentation that we did with the GeoSen of the cratering. And this method accelerates the segmentation and basically enables feature morphological classification based on the ring shape of the crater, if the crater is circular, elliptical, or even polygonal. So it's a very powerful tool. But it's important to note that the segment anything model can also be directly used in Python with tools like Agidal and Rasterio, and this maybe give us more flexibility and control, but also we need to know how to code and understand some deep learning, basic deep learning. So when we are starting, maybe some people may prefer to use the GeoSen tool. We are using both approaches, so we are running some through codes, use these libraries, and also using the GeoSen plugin to integrate into QGIS. And for the case of series, we choose to use GeoSen for this presentation because it makes the process of the segmentation easier. It's more user-friendly and more efficient and work very well to identify the criterions on the on series. However, this interrogation has not been yet extended to Mercury. I'll talk about this later. So here for Mercury, we are currently working directly through Python. I'll talk about the study cases. So as I mentioned before, this toolkit was developed in just a few months ago, and we're still working on it. So for this presentation, we focus on case studies designed to specifically to evaluate the current functionality of the toolkit. So the test case was developed in two complex craters, Haloni and Kepite crater on Sirius, and two Pickering bases in Mercury, Hakamani North Basin and Hadithalad Basin. The digital elevation models that we are using here were downloaded directly from the USGS Astropedia Lunar and Planetary Cartography catalog. And we are using here the raw datasets without any additional preprocess, and this kind of reflects the early stage nature of the implementation of this toolkit. So for series, we are using here the Dow Hummel Global DTM with the resolution of 137 meters. And for Mercury, we are using the Mentager Global Digital Elevation Model with the resolution of 665 meters. I'll talk about what kind of input that we need for the toolkit. So the idea behind this toolkit is to make it accessible and easy to use. For that reason, we designed the input requirements to be simple. So for series, what we need is basically it's a shapefile represents the criterion. So the shapefile can be fully segmented using GeoSen plugin, and this is it's a better way to do this. But we can also generate the shapefile by some kind of extension such as OpenCrater2 plugin for KeyJS, or you can make this manually using a circular shapefile represents the criterion, and also needs the digital elevation model. For Mercury, it's a little different. The crater boundaries are now defined by two circular shapefiles. One represents the ring and one represented the peak ring. And as I said before, SEN hasn't been integrated for Mercury yet, so we are working on the pre-process and fine-tuning for SEN to improve the crater's boundary identification. And the main problem now is because we need the SEN to make the segmentation of the criterion and also of the peak ring that is inside the crater. So we are working on this. And also need the digital elevation model for Mercury. So the first thing that the toolkit will do is to calculate the crater diameter and also calculates the Pickering diameter if it's a Pickering basin. And also we'll find the latitude and longitude of each crater center. We have here the topographic profiles that are generated at user-defined angular. So you can choose here if you want the profiles 1 degree, 20 degree, or any arbitrary interval. So if you choose like 10 degrees, so the first profile will be 10, the second will be 20, and the third will be 30 degrees, and so on. And this is really important because depending on the kind of research and the kind of data that we are using, we may need more or less profiles. And the key metrics such as depth, central peak height, and peak ring height are calculated by direct elevation sampling. So for each profile, we'll have this metric being calculated. There is some difference between these profile constructs because depend on the specific analytical objects for each planetary body. So on Sirius, we need a complete ring-to-ring profile because obviously the central peak is located at the center of the crater, as you can see here in figure 2 of Hellenic crater. Here showing the topographic profiles that are generated using the semi-automated toolkit. And you can see here that we have some points. We have a center point, 2 points in each side of the crater before the wall of the crater, and 2 points a little after the craters. And these are basically the geometric reference points that help give the analysis of these topographic profiles. So they are generated automatically by the toolkit for all the profiles. And for example, for the central peak highest point, will be located at the 2 wall marker points. So these reference points are very important because without this, the code will just take the highest point along the whole profile, and this would be the ring of the crater. So we are using this geometric reference point to help us give what you want to find in these profiles. There is some difference on the profiles we are using for Mercury, because we have a circular peak ring that it's offset from the crater center, as you can see in figure 3. The profiles will extend from the center to the ring, represent half of a full profile. So for the complex crater in series, we are using full profiles, and here each profile will be just a half of a full profile. And this basically enables the measurement of the ring elevation in each radial direction. As I said before, we also have here this geometric reference point for each profile. We have a center point, a point before the ring, a point after the ring, a point before the wall, and a point a little after the crater ring. And the same as work for the complex craters, the area between the point before the ring and after the ring, will be used to find the highest point of the peak ring elevation. This toolkit can now identify 2 distinct depths in peak ring basin. So we have the main depth of the crater that we are calling here D1, but also we can find with this toolkit the secondary depth that it's happened after the ring, and we are calling here a D2. For the validation of these ultimate measurements, we are doing here is comparing the data that we collect manually with the data of the toolkit extract automatically for these craters. And as I said before, here we are only using 4 craters, so it's very limited, this analysis. It's what we got to do for this presentation. You're comparing using the map for this all comparison. And on series, we find this difference between 1.6% for the depths and 3.6% for the central peak height. And on Mercury, we find this difference to be 3.7% for the depths and 4.1% for the peak ring height. I will show here the graphics for these craters. Before this, it's important to note that all these graphics in this presentation are the x-axis show the angle of each topographic profile. First, I'll start to talk about this, the left graphics here. The results are from Ikepato crater on series, and the first graphic we have the y-axis showing the depth of these craters in meters, and in the second graphic below in the left, we have the y-axis the values of the central peak height in meters. We have here 90 full profiles of these craters. You can see that we have these blue lines that show the values that we obtained manually, and also the red lines that represent the values that we found automatically with this toolkit. You can see that these 2 lines are very close to each other, which means the results are good. We are finding the correct values for these parameters. We can see that the blue lines are always a little below the red lines. And this has happened because the toolkit can find the lowest values in the digital terrain model more precisely than when we did. And here on the right graphics, we can show the results for Halani crater, which are very similar for the Ikepato crater, as you can see. And as I said before, this is important because it shows that the toolkit is finding the correct values for the central peak and depths of these 2 craters. When we started to try to create this code for QGIS, our toolkit was finding a lot of kind of elevation inside the crater that were not the central peak. And here we have the results for the peak ring basin. These are the results from Hakamami North Basin. And as I said before, the y-axis, the x-axis is show the angle for each topographic profile. We are using the same color scheme that we used before. Blue is the automatic, the blue is the manual method, and the red is representing the red shows the values that the toolkit found. So here we have 2 graphics. The first one shows the depth of this crater. The second one is showing the secondary depth in the y-axis. And here we have, in the last graphic, you have the peak ring height in meters. Here we are using 36 profiles. half profiles, and you can see that these outro graphics are reasonably close from both and manual. Both approaches, the manual and automatically approach are very similar. And here I have the results for the last basing that they had the basing. We have the same two graphics, but as you can see, we can observe the difference between the manual and automatic values. Mainly here in the x-axis, between 50 degrees and 150 degrees, there is a gap in the first and the second graphic. And this can be sometimes because by the digital elevation noise, or maybe this can be also caused by the placement of the last geometric reference point on the cratering. If it is point that we are doing a little too far out of the crater, maybe if the terrain is rising, maybe when the measurement a high elevation that the cratering itself. So you can do the adjustment in the toolkit to make this last point even placed directly at the ring of the crater. So it is possible maybe this could be a solution for this kind of results. And so the work I showed you before was what I said with my resume, and because of this these results, I tried to do some new some updates and improvements in this toolkit here now in July. So now we can use some individual profiles and result average profiles and the parameters extraction based on this average profile to reduce possible this digital elevation noise. And this new implementation does not aim to replace the previous method, but really to provide additional options for crater topography analysis. So basically, user can select the most appropriate approach based on their specific research goals, or maybe even combining both methods to achieve a more complete result. I find this really interesting. And this makes the analysis more consistent, specifically dealing with noise in the digital elevation model, maybe. And also we apply something really important that is the stereographic vegetation individually to each crater, basically centered in its own crater itself. And this method preserves angle and reduce shape distortions, make it easier to analyze the crater geometry. So I think I'm talking a little too fast, but okay. Here we have this image show exactly this new adaptation of the toolkit with the average profile. This is literally a screenshot from my screen showing what how the toolkit will run. Here I have 10 profiles of Halloumi crater. In white we can see this average profile of Halloumi crater. We have in the elevation and the distance. So in the green box, the toolkit find the highest point of the crater ring. In the red box, we can see that it's the deepest part of the crater. And also the toolkit found the central peak and the highest point of the central peak. And this toolkit have output its CSV file, but here I print the results. So we have here the crater ID. I run this toolkit now just for one crater, but we can run this toolkit for 1,000 of craters if we want. And the estimated diameter was found to be 33.8 kilometers. The total depth was found to be 3 kilometers, and the central peak height was found to be 280 meters. And also we have the coordinates in Latin long for Halloumi crater that as low as 5 degrees north and 10 degrees east. And basically, these are the conclusion of this work. So basically, this QGIS basic toolkit enables semi-automatic morphometric analysis of impacted craters. Initial tests, and I rephrase here, very initial tests on Sirius and Mercury show the ultimate results are highly consistent with this manual measurement that we did. We have made some recent improvements. So now you have such as the average profiles to reduce the digital elevation noise, and also the stereographic projections that improves the geometric fidelity. Also, we are making some integrations. As I said before, this is very new. This work is very new. So we are making the integration of SEN for Mercury. And also we want to make an adaptation for this toolkit for work with simple craters, because it would be kind of pointless to have a toolkit that only work for complex craters. and not for simple, since we can have both of these characters in many bodies. And this is not really hard to do because we make the adaptation using the same codec structure for the complex characters, but basically ignore the parameters like centropic height. So basically what the toolkit would find would be, you calculate the diameter and the depth of this crater using the same kind of profile and ring-to-ring profile. And as I said before, we are aiming to support the crater classification based on the ring shape. And while classifying circular and elliptical craters is relatively simple in Python, and I have some prototypes scripts for this, but it's very hard to classify if the crater is polygonal or not. And identify polygonal rings and the specific geometry presents a great challenge and may take several months for make this implementation if it's possible. And also we aim to extend the application that took for additional planetary bodies. And basically what you want to do now is build a new catalog of well-preserved craters on Sirius and Mercury. This data set will be used to compare the results from the automatic approach using the toolkit with the existing published catalog for these bodies. And for Sirius, we aim to produce a catalog of over 500 craters at least, including both in simple and complex morphologies. And for Mercury, we'll make a first estimate, but we're planning to apply the toolkit to simple, complex, and Pickering basin. And also, maybe we'll do an additional implementation for proto-basin crater types, but this will be addressed later. I don't know if this is interesting, but maybe. And finally, I want to make this code available for the community to use. Probably I want to do this by the end of the year, but this only would include some integrations such as SEN for Mercury, and adaptation of the toolkit for simple crater and some basic morphological classification based on the reshape limit to circular elliptical forms. And this application for additional planetary bodies, and maybe I'll be continue to work on this in the next year to make more implementations. And as I said before, this is very new. There is a lot of things to make improvements, but this is the presentation. Thank you all for attention. I apologize, my pronunciation was difficult to follow at any point. I'm not a native English speaker, but I hope you could understand the main points of this presentation. And these are the references.
All right, thank you for that. I'm just going to say to the room, don't applaud until I unmute the room. Otherwise, it doesn't mean anything. And also, I had actually muted the room and then said that we're running about 15 minutes behind. So whenever this wraps up, that's what we're going to use going forward. All right. That said, we do have 2 questions so far online. First one is Sierra Ferguson, who asks, does the tool, when used on Ceres, only work on large central peak craters, or can it only be used with complex craters?
So as it now that with the so how the toolkit is now, it's only working on Ceres with the complex craters, and also on Mercury, it's only work with Pickering basin.
Right.
This is the question.
I think so. Unfortunately, Sierra is doing 2 meetings at once right now, so can't actually unmute and ask directly, but she does write, yes, that answers it.
Okay.
Next, we have Jamie Riggs, and Jamie, due to your voice, I'm going to go ahead and read this out, although it looks more like a comment as opposed to a question. So to statistically test the angular data to see if they originate from a common probability distribution, i.e., are the 2 curves the statistically the same, I suggest trying the, oh, wow, I'm getting old. I have to zoom in here. Mardia-Watson-Wheeler test and or the Moore's test for paired circular data. So I suggest copying that comment from Jamie and looking up those 2 tests and seeing if either of those would help you.
I will do this. Thank you.
Okay. I see another one online. I'm going to ask, are there any questions in the room first? All right, then next we have a question from Christopher Brooks. thanks for the talk. Very interesting. Are you considering adaptation for the very craters slash basins? Christopher, you might want to unmute and ask your question directly.
Yes, sorry, my apologies. I realized I didn't put enough information in the question. The reason I'm asking about adapting it for the very large craters and basins that we have on Mercury, places like Colorus and Sobku, where they may not have necessarily much internal structure like peat rings or things like that, but can have quite uneven floors, and the rims can be quite quite difficult to define in places. I'm wondering whether or not you have any thoughts on the matter.
So, yes, I have been thinking of work with these more complex craters. I didn't have the time. As I said, I want to do this implementation from proto-basin, but maybe we're also thinking about using this kind of method for large craters, because the only thing that we need to do for these large craters is put more geometric reference points. So maybe I think it's possible.
Okay, thank you very much.
All right. While I wait another 30 seconds to see if there are any more questions by talking slowly, I am going to emphasize again in this room, the ceiling microphones are very sensitive. They can pick up any side chatter. So folks online can hear you just as well as everybody else who's talking. So just be aware of that going forward. And I think I've vamped long enough. Seeing no more questions, let us thank our speaker again.